Sure, sure.
Okay, so now we'll have the second lecture of Marcos Mariño on Resurgent methods in string theory. And please keep asking questions, but also wait for the microphone. Thanks.
Okay. Okay, so let's resume the discussion yesterday. Let me just remind you two pieces of information to resume the discussion. So the first one was this calculation of Stokes automorphisms. So if suppose that you have a ray here, a Stokes ray, with many singularities that are labeled by omega, so labels the singularities. And we found this nice formula which calculates the discontinuity of the Borel resummation. And, you know, I think yesterday I only wrote a single, what happens when you have a single singularity. Remember that we are computing the difference between resummations along these two paths. And the formula that we get is something like this. So this is the Stokes constant. Then you have the location of the singularity, and then you have the resummation on below of omega z, okay? And remember that phi omega z for a generic branch cut singularity, we have something like this, where this is just nz, sorry, n bigger than or equal than 0, sorry, cn, and then z n minus b, okay? So this was one way of finding the information of the singularity. Here we have the location of the singularity, the Stokes constants, and the full series. And remember also that when you have, you know, if we have here the first singularity, you know, you can think about this as determining the large order behavior of this an. So we have something like s omega, maybe up to some factor of 2 pi, and then we have the location of the singularity to minus k minus b, k gamma k plus b, and then, you know, we have the full series of corrections associated to this. So we have n plus k plus b divided by gamma k plus b, and then a to the minus n, or n, sorry, let me call this the leading singularity A. So A is the location of the leading singularity. And then I have here A to the, just check that I'm not writing anything wrong. Yeah, this is A to the n. And this is, sorry, this is minus n. K plus b minus n, okay? So these are the two kind of methods to get information. One is the discontinuity, and the other is this. And today we are going to use this in physical examples. So let me first make a comment. So this formula, it's quite interesting because it shows, in a sense, what is the natural object that appears when you study resurgence. So here we started with a perturbative series, so we have this perturbative series phi z. But when you do this type of calculations, you end up with very interesting combinations. You have also series in z, but they come with an additional exponentially small factor. So you can actually think about the series as containing two small parameters. One is z, which is the variable in which we span around, which is a small parameter, but another small parameter is e to the minus zeta omega over z. So if this has a positive real part and z is very small, this is very, very small. So we can think about this as a small parameter, which is in principle invisible in standard Taylor expansions, okay? That's why this is the kind of thing that is invisible in perturbation theory. And these type of combinations in which you actually have these two types of terms, this type of series in which you not only have one small parameter, but additional small parameters of the exponential type are called trans series, okay? So the typical trans series is, let me write it like this, phi of z is going to be typically starts with the standard perturbative series that you have computed, and then you will have a general linear combination of things like this, okay? So this is the typical Tron series. And then this is the kind of objects that you can resum. Here, for example, we are considering Borel resumations of this series phi. Here we are considering Borel resumations of this series phi omega. So in principle, you could actually calculate Borel resumations of this big object. And these are our candidates for non-perturbative functions, okay? There is a lot I can, one can say about this thing. So today we will explore a little bit this story, but there is sort of complicated casuistics that, if you want, we can discuss in the question session or later on. I will give you anyway some examples today of how these Tron-series work, okay? But this is very important. The idea is that you should be able to reconstruct observable in physics by adding to the perturbative part some additional exponentially small objects, and this is what I call sometimes semi-classical decoding, in the sense that we are rewriting an exact result in quantum field theory, quantum mechanics, or in string theory as a resummation of an object like this. And it's important to distinguish the two levels. This equation is purely formal. These are not numbers or functions or anything. This is just a bunch of factorial divergent series. So this doesn't make any sense as a function. It makes sense as a formal expression. And then by doing Borel resummation, we convert this formal expression into an actual function, okay, if the right conditions arise. And this is what we are going to use as a candidate for non-perturbative functions, okay? So I have spent a lot of time giving you a lot of framework, mathematical framework, but now I want to discuss examples. So before entering into a concrete example that I want to discuss, let's actually give some sort of roadmap of non-perturbative effects in physics, okay? Non-perturbative and perturbative effects in physics. So let's start with the simplest example, quantum mechanics. Now, in quantum mechanics, there are two types of series. There are series in the coupling constant, okay? And here, the AN grow like n factorial. But there is also something that you can do, which is calculate series in the Planck constant. So this is perturbation theory in a coupling constant. And this is, let me write it like this, AN h to the 2n. This is WKB, expansions. And it's interesting that this already has a double factorial growth, which you will later find in string theory. But, this is actually already happens in WKB, okay? Now, the non-perturbative effects, if you do resurgent analysis, the non-perturbative effects here are typically associated to instantons, okay? So if you want additional saddles of the path integral. Also, the story is more complicated than it looks, but let's say that these are going to be instanton effects, and today we will see an explicit example of this. Now, what happens in quantum field theory? Well, you have the perturbative series, okay? And again, the typical growth is like n factorial. And here, the non-perturbative effects can be of two types. You can have instantons, but what are much more common are renormalons. Here, these are related to saddles of the path integral, as in quantum mechanics. Now, renormalons are a little bit more subtle, so this is actually the default. So the default case, when I say the default, means that if you give me, say, Yang-Mills theory or, your favorite, for example, asymptotically free quantum field theories, they will have, the non-perturbative effects will actually be dominated by renormalons, not by instantons. Now, renormalons do not really have a subtle description. There have been proposals, but, these are, at the moment, just proposals. But in some cases, they are related to the OPE, the operator product expansion. and two what are called condensates. So these are actually non-perturbative effects with no saddle point description. And this is very important. It's very important to keep in mind that there is a very important family of non-perturbative effects without being implemented explicitly as saddle points. Now, in string theory, we have this tendency to believe that everything which is non-perturbative is going to become from a saddle. That's not even the case in standard quantum field theory. Okay? So one should be aware of this. Okay? Now, there is something else in quantum field theory, which is the 1/n expansion. Rajesh has talked about this. So in the 1/n expansion, what we do is, as Rajesh was explaining, well, we have something like this. Let me use just string theory notation because, and then, you know, for matrix theories, so this is for matrix theories, there are also vector theories, which is very important. You have something like this, and remember that Fg of t is obtained by summing, so T here is the tough coupling, I guess. I don't know if, I mean, I'm going to write it like this. I mean, in Mills, you know, identify this as G squaring very gauge series. And then, you know, here what you are doing is essentially sum a series over the tough coupling, right? So you sum all the diagrams of genus 0 for each h. Now, this series is convergent, has a finite radius of convergent in lucky cases, okay? So lucky cases are the cases that we like n = 4, Chern-Simons, ABM. But in general, this series is divergent due to the renormals. Okay? So, so it's only in, I mean, you know, Toft proposed to use the large n expansion to be able to get convergent sums, but one has to be aware that this doesn't work in general. It works in the cases that we like, but not in general. Okay, now, when this is convergent, another important thing is that when this is convergent, the FGs have all the same radius of convergence. At least in all cases I know, this is the case. And this is very important because this means that you can fix t, you can now fix the value of t inside this common radius of convergence, right? You can do that, again, in this convergent case. I'm just restricting to this convergent case. This divergent case is slightly more complicated. Let me not address it now. But if this is convergent and there is a common radius of convergence, you can fix the value of t inside the common radius of convergence and think about how these coefficients grow as you vary the genus, right? As genus increases. And the answer is that these FGs of t for this fixed t are going to grow like 2g factorial, okay? And that's the generic growth in 1/n expansions. So we get, so you see the trade-off of Toft is tricky because, yeah, on one hand you can get sometimes, you know, things are good convergent things, but then, you know, factorial divergence will hit you back when you try to resolve the 1/n expansions. And the non-perturbative effects associated to this are not that well understood, I would say. I call them large n instantons. Sometimes you can build up these, the non-perturbative objects that actually govern this 1/n large n factorial divergence. You can build them from standard instantons, but this is really a much less explored story. Today, maybe tomorrow, I will actually give you a beautiful example of a large n instantons in matrix models where you can actually make this very precise. But in, say, Mills, you know, what is the kind of configuration responsible for the factorial divergence of the 1/n expansion? I don't think anybody has a very clear idea what it is, okay? Even in Chern-Simons. Well, in Chern-Simons, there are some sort of, yeah, you can do something about it, but say on the 3 sphere or things like that, okay? But yeah.
But is there a complete understanding on?
Well, the thing is that in Chern-Simons you have this multivalueness of the Yeah, I mean, from the point of view of field theory, it's slightly subtle, yeah, I would say, yeah. Now in string theory, so this was in QFT, so in string theory, what we have, it's again, amplitudes, let me write them like this, So you will have the string coupling constant and modulus. Of course, just simplifying my life, with, something simple. So again, this will have a very similar behavior, of course, as 1/n expansion in matrix gauge theories. I'm going to write it like this. So this is the string coupling constant. And again, in cases where we are happy, these objects are well-defined functions of T. They have a common radius of convergence. And inside this common radius of convergence, one believes that these things should behave like 2G factorial. So again, you have a 2G factorial divergence. And the non-perturbative effect associated to this are supposed to be the branes. Okay? And notice that large N duality should relate this picture of 1/n expansion and large N instantons to the factorial divergence of the genus expansion plus the non-perturbative effect due to the branes. Okay? So this is more or less like the general roadmap. And as we moved from quantum mechanics to string theory, things become less and less clear. And I don't think we really have a complete understanding of many of these things. I mean, many of these things, for example, the role of renormalons, what happens with these large N instantons, all these things, this is more like what we believe than having really very precise examples, very precise theories. Even in examples, we have very few examples, we understand all these things carefully, okay? But today, what I'm going to do is to give you a very simple example of resurgence in quantum mechanics, which was in a sense the founding example, okay? Questions so far? Yes?
I was curious if there's something like a nice picture on the Stokes plane about the different phenomena that are e to the minus 1 over gs versus e to the minus 1 over gs squared, or something like e to the minus n, e to the minus n squared.
Yeah, this question recurs. I don't have any evidence about this 1 over gs exponential of minus 1 over gs squared effects. I'm not going to discuss them. We discussed with Rajesh yesterday, this might be related to the divergence, not of this series, but of the sum overall trans-series, okay? This might be a kind of additional layer, okay? But we're not going to discuss this in these lectures. Okay, so let's start. Now, so the sample I'm going to tell you, yeah, sorry.
Is it the case that you don't have things like renormalons in string theory, or you just haven't found anything
That's
yet?
a very good question. The thing is that in string theory, the boundary, usually we make a very strong distinction between instantons and renormalons. And people say, well, instantons are due, these are factorial growth. So what is the source of factorial growth? So there is a lot of heuristics here. There are very few. So the heuristics is instantons are due to the factorial growth in the number of diagrams, okay? Now, renormalons are due to the factorial growth of the integration over Feynman parameters, okay? That's what the picture. But you see, one interesting observation is that in string theory, this distinction is actually very, very, very difficult to maintain. Because in string theory, you could say, okay, there is no proliferation of Feynman diagrams. There is only one Feynman diagram for every genus, and everything comes from integrating over the moduli space of Riemann surface. So you would say that factorial divergence in string theory is more of the renormalon type. At the same time, we have saddle point descriptions of things like this. Well, in a sense, the branes is a different type of non-perturbative object at instantos. I mean, they are coming from boundary conditions and so on. You can think about them as saddles in string field theory. But you see, it's in string theory, the distinction, it's a little bit more murky. So sometimes I like to think about this as coming from integration over moduli space. So this is more like a renormalon type of effect. And sometimes I would like to think about this more like coming from a saddle, so it's an instanton. So I think in string theory, this is still to be clarified.
Thank you. Thanks.
Very good. So let's see then our quantum mechanical example. So yesterday we did lambda 5 theory in 0 dimensions, and today we are going to progress and do lambda 5 theory in 1 dimension. So we are going to consider something that you might have done in undergrad courses, which is the quartic oscillator, okay? Because this is the simplest example in quantum theory of a divergent series, okay? So the quartic oscillator, we are not going, yesterday we looked at the partition function. Here we are going to look at something slightly different. We're going to look to the energy of the ground state, okay? So you calculate the energy of the ground state. You know the first term is 1/2 here. I'm taking h equal to m equal to 1. So this is a particle in relativistic quantum mechanics. So this is the 1/2 that comes from the ground state of a harmonic oscillator. And then if you do the calculation, you will get 3g/4. Maybe you did this calculation as an undergrad in courses of quantum mechanics, stationary perturbation theory. Then, you know, the next term, you know, you probably didn't calculate it, something like this. And then you have a series. And then what they didn't tell you in the course of quantum mechanics is that this series diverges. You see, it's a typical example. So this is, let me write this as this. This is a typical example of a divergent series in quantum mechanics. Okay, so this grows like the n factorial. Okay, then Bender and Wu in 1970 they asked the following question: what is the precise growth of this series? So we are talking about 1970. So you know, Bender and Wu were physicists. They knew that it would be a very hard theorem to prove mathematically to derive this. So they did experimental mathematics. They generated 70 terms of this series. And to do that, they invented, of course, you know, if you do the standard method that you find in the standard book quantum mechanics, you will never get to order 70. So they invented a very clever method to do perturbation theory, which is now, by the way, implemented in a very nice program that Suleiman Pasic and Unsal wrote to do calculation quantum mechanics. It's called the Bender-Wu package, okay, where you can calculate series to very large order. And, but at that time, you know, of course, you know, I don't know what kind of computers they had in 1970, so they generated 70 terms, and they studied their asymptotics. And amazingly, they got the right answer. They got a very nice formula, okay, which is the following. Let me write it down. So that's the type of formula that they got. So this is the behavior for n very large. And you know, this is a formula that actually I encourage you to do by following the mathematical package that I gave you in the lecture, for the lectures. It's called quartic oscillator or something like that. And there, I give you 200 terms of this series. And then you can study this large order behavior using numerical techniques. And then you can get even this number with quite a lot of precision, 22 digits. If you put these 22 digits in Wolfram alpha and you tell them to recognize the number, it will give you this number. So that's the nut. I mean, I did the experiment the other day. And you know, this is, you can redo the steps of Bender and Wu, but of course using much more sophisticated computer power that they had at the time, okay? Now, but let's look at this formula. You see, if you look at here, you see that this is exactly the type of standard formula that we would expect. And now you can start to read what is going on here. Now, remember that any large order growth formula can be rewritten as a formula for a singularity in the Borel plane, right? So A gives you the position of the singularity. Here we have 3n minus 1 to the n. So this means that in the Borel plane, let me write it here, there will be a singularity at minus 1/3, okay? Okay, that's the first thing you realize, okay? And you see here, 1/2 means that B here is 1/2, so there is going to be 1/z to the 1/2. So let's actually write down the trans series associated to this that you could get. this is a function of the coupling constant. And then, if you are careful, well, you will get, first of all, you are going to get 1 over 3g, okay? And then here you are going to get, if I remember correctly, you're going to get twice over pg, okay? And then this will have corrections in g, okay? So this is the series that you will attach to this singularity, and here we have a branch cut 1/2, okay? And so this is what they found, okay? Now the question is, what is the interpretation of this transeries? What is the meaning of this? After all, this quartic oscillator, well, doesn't look very, very dramatic, right? You have here a potential like this, and then, there doesn't seem to be many interesting non-perturbative physics. But then, what van der Amburg realized is the following. Well, you see, after all, these are formulae for complex variables, so this should also be describing the physics, when G is negative, okay? But when G is negative, the non-perturbative physics of this model changes drastically. Because when G is negative, what happens is that this potential, when you change the sign of G here, this becomes an unstable oscillator, okay? So you change the sign of G, you will get an unstable oscillator. So let's try to redo the analysis when G is negative. Now, when G is negative, nothing changes here except the overall sign, right? I mean, you change, this is the behavior of AN is multiplied Gn. So you now take G negative, you will get a series in which the coefficients are non-alternating. So in principle, the Borel plane for this theories is going to be the same. It's just that you're going to change everything sign, so you're going to be here 1/3. And now you will have this series here. Now, maybe with some factors of I, but let's not worry about overall factors for the moment being. You will have something like this of Pg. So let me actually write it like this. So here now I assume that G is negative. And then you will have here e to the minus 1 over 3G, okay? So now you have really an exponentially small amplitude. And it's actually very easy to interpret this because we know that in such an unstable potential, what happens is that, you have tunneling, okay? So if you have a particle here, it will eventually tunnel there, okay? Now let's do a semi-classical calculation of tunneling in this potential. So let's suppose that we are at zero energy. We have, you want to do a calculation for the ground state. Classically, the ground state has energy 0. So you have to consider the tunneling as in WKB, for example, you would consider tunneling from this point to this point to this turning point. Let me call this X star. And then you can get an estimate, in WKB, your estimate of the tunneling amplitude will be like this, where S is actually the period for, for example, in the instanton Peter, you would have a particle that goes here and then goes back. So you would have something like this. So you would have a cycle. Let me use color choke. Have a cycle like this. So this would be cycle gamma. And here you would integrate the momentum. And, if you do things, explicitly, you will get this integral. And then, you will have here 2 dx. And then you do this integral. It's an elementary integral. And what you get 1/3. Okay? Which is precisely the location of this singularity. Okay? So so this is actually very interesting if you put everything together. So we have this problem here. We found that this series diverges factorially, but then with this factor 3 to the n, there's a singularity here, and this singularity has an interpretation. Is the exponentially small type of behavior that we would have in the problem if we change the sign of the coupling constant and we have an unstable situation, okay? And then, the value of the location of the singularity can be computed very explicitly by WKB techniques. And, let me actually make a point something here. This is a period of an integral, I mean, if you think in very kind of high mathematical mode, you see that this is the period of a meromorphic differential, okay? Period of a differential. And it turns out that, as I mentioned yesterday in the question session, this is going to be a pattern that is going to be repeated in many examples, okay? But already in quantum mechanics, the locations of singularities are periods, okay? And that's periods of actually the Liouville one form associated to the problem, okay? So this is going to be a pattern that recurs. And now another thing that another thing that we should understand in this situation with inverted potential is that now the energy, the ground state energy, will not be, I mean, you don't have bound states here. So what you have are resonances. This means that the energies will have an imaginary part, which is inversely proportional to the lifetime of the particle in this well, okay? Particles tunnel, there is a lifetime. This is like radioactivity, right? And then, the way you calculate the lifetime is by calculating the imaginary part of the energy. So there is an imaginary part of the energy, okay, which precisely goes like e to the minus sg, okay? Now, what is interesting is that you can revisit this relationship from the point of view of resurgence. So remember that here we have a singularity here, so we can actually consider, you see, the series when G is negative will have a singularity here. I mean, the Borel transform will have a singularity here. So if you try to do the Borel resummation of this series along the positive real axis, you will find an obstruction in this singularity. So you have to do this deformation that we have. So it turns out that these approximate relations is going to become an exact relation. So let me actually write it for you. So what we have is that there is a difference. You see, notice one thing. The imaginary part of the energy by WKB is exponentially small, okay? We know that this difference is also going to be exponentially small. This is just an approximation, approximate calculation. But it turns out that if you do the calculation cleverly, you can see that you can get here an exact expression, and the expression is that the discontinuity of the Borel series, let me call this, let me call this series phi of G, okay? The discontinuity of the series is actually twice I, the imaginary part of E0, okay? So this is an exact formula which tells you that you can calculate the imaginary part of 0 exactly by calculating this discontinuity, okay? So this discontinuity is going to be purely imaginary, okay? And this is actually giving you twice the imaginary part of the energy. And in the program, you are actually encouraged to actually check this relationship, because on the other hand, if we look at this formula, we know that this discontinuity is going to be at leading order, is given by the contribution of the first singularity. So actually, this is going to be, is given by this series, so twice 2 over PG e to the minus 1 over 3G, okay? And then you can, notice that now we have even the prefactor. Here, the WB calculation gives me the exponential thing. Here, by doing this analysis of the singularity, you can even get the prefactor, and you can actually check that this formula is actually correct. You can actually calculate these Borel resummations. In the program, you find a section where this is done. You can calculate this discontinuity numerically and check that this is actually approximately given by this, okay? So this is an exact formula. So this is actually one way in which you see that the perturbative series contains non-perturbative information. We started by this very kind of trivial problem, and suddenly we're having information about instantons, tunneling. If we didn't know about tunneling, which is the quintessential quantum phenomenon, if we didn't know about tunneling, researchers would tell us there is tunneling. because the singularity means tunneling, actually. This singularity means that there is tunneling in this potential. And you can even get this sort of formula. Do you have a question?
No, I mean, even WKB also would give you the prefactor also.
Yeah.
But does
let me tell you something which I think is important. Many of the formula that you find in the books on WKB are wrong, including Lambda and Lifshitz. Okay, and this has been known among many people. And the only way to make this formula actually correct is to use Borel resummation techniques. Already WKB, I was actually quite shocked to know that there is a wrong formula in Lambda and Lifshitz, but there is. and there is a very subtle reason. The reason is that if you want to calculate prefactors correctly in WKB, you have to take into account a piece that comes from the all orders expansion of WKB. So actually, I already wrote, you have to actually do the calculation at all orders in H bar. And there is a contribution that has to be resummed, which actually is crucial to determine the right prefactor. And this was never done until people understood Borel resummation properly. So WKB is the kind of very standard story, started in the 20s, that only got clarified, according to my view of the history, in 1980, when Voros actually wrote his famous paper on the exact WKB method. Until then, WKB was a total disaster, where people fighting, having all kinds of controversies, There was this paper by Silverstone, who was a quantum chemist, who actually got also the same formula than Voros. So this guy tried to publish his paper. All the WKB establishment, which was doing wrong calculations, actually tried to block the publication of this paper. It was actually an amazing controversy. So, So you see that, you want, Borel resummation is even crucial to understand, WKB properly, okay? So the prefactor here, if you want to calculate it, is very subtle, okay? If you want to learn about this, I can recommend you my own book on advanced topics in quantum mechanics. And there, all the prefactors are correct.
Sorry, I'm a bit confused about this 1/3. So here G is negative, and you're expanding around G is equal to 1/3, or?
Sorry?
So, sorry, this 1/3 is the value of G that you're expanding around, right?
Yeah, sorry, here I have to say, it's G in absolute value, yes, like here, yeah.
So in this, here G is negative, and you're expanding around.
Here G is negative, so we have minus, if you want, I have minus G in absolute value, and then, here, here also is in absolute value, absolute value,
And in this picture also, this is for mod G, or it's G?
Yeah, this is when G is negative, So I wrote it with the absolute value of G, so that, but it's just, I'm just changing, I'm just using this formula, just changing the sign. If G is negative, this is going to have with a minus sign, and then 1/3G, if G is negative, is minus 1/3 is absolute value of G. Okay.
Okay.
The formula is the same. And why is the same? Because it just came from the same series, right? You cannot change it. The series is just to pick a minus sign, right? And the minus sign is just coming from G. So the coefficients are the same for positive and negative G. That's the important thing. The perturbative series has the same coefficients, right? So.
And this 1/3 you got by doing Borel resummation and everything, or is?
Sorry?
You got this minus 1/3 and 1/3 by doing?
No, this comes from large order. Here I didn't do anything. I didn't do WKB.
Right.
I said that if you have this information, the information of the transeries, it's equivalent to the information in the large order. So just by knowing the large order of behavior of these coefficients, I can already write this non-perturbative function. Okay?
The fact that there is a singularity at minus 1/3, that
comes from already here. Because, this is the signal of a branch cut. What is B here? The shift of B here in this formula is the value of B here. So this is already the square root branch cut that you will have here. So, that's the power of resurgence. You just look at the perturbative series and you can already write down this. I don't need WKB. If I didn't know about WKB, I could get this formula anyway. I'm just saying that this formula can be reinterpreted via WKB. But the important thing of resurgence is that if I knew, imagine that, quantum mechanics was not developed, I didn't have the Schrodinger equation, but I have an algorithm to calculate the perturbative series to all orders. By the way, this is the situation in string theory. In string theory, we don't have a Hamiltonian for the string fields, but we have an algorithm to calculate the genus expansion. So imagine that, you give me this algorithm, okay? And I can calculate this series. Just by using Resurgence, I will be able to get this result and to get the result. I wouldn't need anything else. And then I would have to think a lot in order to understand what this means in my incomplete view of quantum mechanics. But that's the point. Even if I didn't know about tunneling, this large order behavior would tell me about tunneling. Okay? Okay, so now let's go back to this situation. Now here, you see here when G is positive, there is no obstruction to Borel singularity. Okay? Here you could actually do the Borel resummation here, okay? And, the two lateral resummations will be the same. So there will be a well-defined object, which is just the resummation of phi 0 for positive G, okay? And actually, this is equal to E0 G exactly. And this is the upgrade of optimal truncation. If you were using optimal truncation with this series for sufficiently large values of G, you wouldn't be able to get an exact formula. But if you use Borel resummation, you actually get exactly, you will get exactly this identity. And actually, again, in the Mathematica program, I actually wrote a very simple code that calculates this Borel resummation. With 200 terms, this can be done with a lot of precision. And then there is another code that does the calculation of this using Hamiltonian truncation, okay? Which calculates, and you can see that these two things agree at the numerical order that you can reach, which is, 20 decimals, okay? So this is an exact statement. And this is where you actually, thanks to these Borel techniques, you can find a way to improve your treatment of asymptotic series. And you can really get, remember, we started saying these asymptotic series do not make any sense because they have just a convergence 0, but now we know that we can actually not only get information from them, that we could even do with optimal truncation, but we can get exact information. No error here. You see, this will you will never achieve with optimal truncation. Optimal truncation for any value of G, there will be an intrinsic error. And here, this is an exact result, okay? Yes?
So yesterday you were saying also about the fact that Resurgence would not give us all the time the completely exact answer. Is this a special example where Resurgence is enough to give us the fully non-perturbative, including all the instantons and everything?
Yes, I mean, the thing here in quantum mechanics, essentially, it's a place where you can essentially find the Resurgence gives you all possible sectors, okay? There are some exceptions, okay? There are some exceptions, but in this case, this is a lucky case, of course, there are unlucky cases, of course, but this is the lucky case in which, Resurgence tells you first, what happens when G is negative, so you have tunneling, and also when G is positive, it tells you how to reconstruct this exactly, okay? So that's true. There are cases, for example, in the double well, in the double well potential, Resurgence tells you that there are instantons, but it misses the first instanton. It goes already to the instanton and anti-instanton result. So you can have these sort of problems also in Resurgence. But in WKB, it never fails, Resurgence, okay? When you do WKB expansions, you always get everything from Resurgence. That's also important. Okay, so this was the example I wanted to show you. I mean, we can discuss maybe, if you are interested, we can discuss the program that I wrote for you so you can look at it, and then, if you are really interested in seeing how this works, I can show you in detail how the program does all these steps. It's a good exercise if you really want to have a hands-on example of Resurgence, okay? So this is the standard story for this Bender-Boo problem, and now we are going to jump to string theory. So let's now start discussing then string theory in some detail. So, Francesco, what time is this is 12:13, right? Okay, very good. So you see one crucial thing of this Bender-Boo calculation was to actually have tons of coefficients of the perturbative series. That's in a sense, one of the limitations of Resurgence, that you really want to make it work very well, you need to have a lot of coefficients of the perturbative series. And in string theory, this is not very easy, right? I mean, people are still fighting with doing calculations in string theory at 2 loops, right, in generic superstring theories. So a very important development in this sense was the non-critical string theory revolution in the early 90s, where people for the first time were able to actually calculate string series, genus expansions, at all orders in the genre, okay? And the way they did that, well, was by using this double scale matrix model. So there was like, in a sense, an early example of large n dualities. And I have to say that in principle, large n dualities also make life easier in order for doing Resurgence, because they give you also more control over the perturbative series, okay? So what was the non-critical string theory revolution? Well, people look at very special models of, so they look at actually 2D CFTs coupled to gravity with the central charge less or equal to 1, coupled to 2D gravity. And they were able essentially to solve these models, okay? So of course you see big limitation here is that the central charge is very small. So these are strings in 1 or less dimensions. So actually, I'm not an expert myself on the kind of continuum theories of 2D CFTs coupled to gravity. So we are going to focus on the simplest case, which is actually the theory in which there is essentially no matter, C equals 0. This is called sometimes the 2-3 minimal model coupled to gravity. So this essentially, from the point of view of matter, this has no degrees of freedom. And essentially, this is what sometimes this is called pure gravity, okay? Now, what you can do is to actually compute the free energy. You can actually try to consider the free energy. Let me actually mention that this theory, this pure gravity, has only one parameter, which is the cosmological constant K. So this is the actual cosmological constant that appears in gravity, okay? But actually, one important result here is Nitschik-Poloachikov-Samolotchikov scaling. And according to this scaling, Fg here, so if you want to calculate the free energy of this theory on a Riemann surface, connected Riemann surface of genus G as a function of kappa, what you find is that this is going to be a number, a pure number Cg, and then you will have this dependence kappa to the gamma 2 minus 1 to the 2G minus 2. So gamma is sort of a critical exponent. It's called string susceptibility. I mean, I'm just reviewing these statements. I actually would have a hard time right now to justify all of them. So let's assume that ChatGPT tells me that all this is true, okay? Which is true. And then, we are going to focus on our goal here, which is to understand the large genus expansion, okay? Now, for this theory, for pure gravity, this is minus 1/2. But what is important here is that this scales like something to the 2G minus 2. This means that, of course, this is going to be multiplied by GS to the 2G minus 2, but it's clear that I can reabsorb GS into kappa with the appropriate value. So I will actually think about the free energies as functions of kappa, and the total free energy, F of kappa, is going to be just the series of the Fg kappa. And you see that this is such a simple theory that I have no moduli, essentially. I mean, I only have one moduli, the cosmological constant, but this can be combined with the string coupling constant. So the only thing that I have to compute are these numbers Cg, okay? Now, the question is, how do you compute these numbers? And again, this is something that in string theory directly is very hard. You can do maybe genus 0, genus 1, but if you want to do it at all genus is very hard. And this is where duality with matrix models of the type that Rajesh has been explaining has been extremely powerful. So what people did was to find this answer. So I'm just going to give you the answer because that's what we want to understand here. It's not so difficult, actually, to do this. So this was work by Grossan, Migdal, Brezan, and Kazakov, and Douglas and Schenker. And what they found is a very beautiful thing. So what they found is that the following. Now, let's take the second derivative of this energy, which is a function of kappa, and this is called sometimes the specific heat. I mean, this is just I mean, there is no heat here. Eh? This is just an analogy, right? And then what is very important is that this specific heat satisfies the Pain-Levé-1 equation. Okay, that's the main result. This function satisfies this Pain-Levé equation, so this is a non-banana object, as Lara would say, because it's a nonlinear ODE. So it's a nonlinear ODE, and this will be important later. And what you have to actually tell me is what are the boundary conditions. So the boundary conditions is a calculation at G0 that you can do, okay? And this is that when kappa goes to plus infinity, this goes like this, okay? But now, you know, this is a cheesecake in order to compute the genus expansion, because you just plug, you know, you just now use the Pain-Levé equation and calculate, and everything follows. So, so this is something that you can do very quickly in a computer. So let's assume that U kappa is kappa to the 1/2. And let me just already write it like this. UG, and now you see how the, so you will have this scaling here, okay? So you will have -1, 4, -1, which is -5/4. And then you will have this thing here, 5G/2, okay? And then you plug in this here, and you just expand, and you get everything. And you can even write a recursive relation. And I wrote another mathematical package for you. It's called Pain-Levé-1, I think, where you can actually generate this, you know. This is, you can generate to any genus you want. You can, I think, you know, in few seconds you generate 300 genera, okay? So you actually get a very nice result. So, you know, you can see that this goes like 1 -1/48, kappa to the -5/2, blah, 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 blah. And then when you plug this into the F, into the total F, you get a -4/15 kappa to the 5/2. There is a logarithmic part here. This is the genus 1, which is always an outlier. You have logarithm of kappa. And then, for example, you have the answer for genus 2, a beautiful number, typical of 2D gravity, which is kappa to the -5/2. So this is already a non-trivial result if you want to get it, you know, you want to get it directly. Of course, you know, then people discover, you know, Kontsevich model and so on, and you can actually, this is the standard number that you can get by intersection theorem in the model space and so on, okay? But Pain-Levé-1 gives you everything, and in particular, you see, once you have a nonlinear ODE, you can solve it by recursion. You can write a recursion relation with these coefficients that you can find, you know, I wrote it down in the lecture notes, and now you can, you know, since you have such a control of the theory, you can actually say, okay, how are these UGs going to grow? Well, already a very quick look at the recursion gives you a very quick answer that this is going to grow like a to the -2g, 2g factorial. And actually, a you can get from the recursion is very easy. A is a number, 8√3/5, okay? And let me actually point out that since this is a series in even powers of GS, okay, or even powers in kappa to the -5/4, you actually, you will have here two different singularities here. You have always the singularities in these theories, in string theory, since the genus expansion is in even powers of the coupling constant, they always come in pairs, okay? So, so that's something that, you know, is good to keep in mind, but I usually will write just results from one of the singularities, okay? Now, another thing you can do, and this is again, you know, the same sort of, you can now repeat the exercise on Bender and Boole in quantum mechanics for this 2D gravity series, okay? So you could try actually to improve. This is a rough asymptotics, okay? You can try to improve it with numerical techniques. Again, you have generated 200 terms, 300 terms, so you just do this numerical analysis, and then you get an improvement of this. Let me write it like this. You will get something like this. S of pi, S is a Stokes constant, A minus G plus 1/2, gamma to G minus 1/2. And then S, again, is a crazy number. Remember that before was square root of 2 divided by pi to the 3/2. Here you have minus 3 over 1/4 divided by 2 square root of pi, okay? So these are these crazy Stokes constants, which is the hard part to calculate, okay? And I will actually explain this in a moment, why this is the hard part to calculate. But again, we can now use the fact that given any large order behavior, I can route immediately the trans-series associated to the leading singularity. So here, there will be a leading singularity here. Let me point out that there are singularities all over the positive real axis at multiples of A. And you will see also this as a very easy consequence of what I'm going to say. But we can now write phi of A, of kappa. And then, you have to be careful here because there is an overall factor of k to the 1/2. And you also have to be careful here because what we call Z there, if you want to keep things, so it is a little bit confusing in the sense that you have to be careful because Z is kappa to the minus phi over 4. There are all these crazy exponents going around, but nothing is nothing important. So you have here minus 1/2. So this means that we'll have here Z to the plus 1/2, but Z to the plus 1/2 is kappa to the minus 5 over 8. So there is have here minus 5 over 8. And I have here exponent of 8 square root of 3 divided by 5 times 1 over Z, which is kappa to the 5/4, okay? And here it is, our first non-perturbative effect in string theory, okay? Just coming from the genus expansion, okay? Now, as I said here, you have a recursion, which is complicated. You can analyze this, numerically, and you get this. But now, the question we should ask is, can we do better than this? After all, we have this wonderful ODE, right? So can we do better than this? And the answer is yes, we can do better than this. And to do this, we are going to exploit the existence of an ODE. Okay, so let's see how this goes. Okay, and the idea. I'm going to give you sort of idea, and then this idea can be justified mathematically very precisely. But the idea is the following. Okay, since there are these non-perturbative effects, okay, this is in a sense an exponentially small correction to my perturbative series, right? You can think about it as a exponentially small correction to that. Okay, so yes, sorry, yes.
7 over 5760 is the coefficient of the A hat genus. It's the P1 squared coefficient of the A hat genus on in the index theorem.
I see. Wow.
I'd seen it before somewhere.
I see. These coefficients are actually special types of integrals over the modular space of Riemann surface. There is actually a very nice paper by Itzigson and Zuber where they actually wrote down the exact correlator in 2D gravity that gives you these numbers, okay? So maybe it's related. We know that these correlators are related to, I guess this genus is related to 1 over sinh and 1 over tanh or functions like this.
It appears in the Atiyah-Singer index theorem. It's the degree, one of this coefficient of 2 of the characteristic classes of degree 8, which is P1, P1 squared and P2. That's the coefficient of the P1 squared term.
Yeah, it's a Bernoulli number. Yeah, I would say that it's related to something like that. That's why I say it's probably related to the fact that this comes from 1 over sinh or something like that. Yeah. So, yeah. Okay. So yeah, sorry, here, I mean, you can put plus or minus because I say there are two singularities. But now let's try to do, I mean, this is the kind of numerical approach, but let's try to do something a little bit more clever, right? So let's then assume that U kappa, the solution of pan level 1, let me write it as U0 of kappa, where this is the perturbative series. And now let me write something that I'm going to call a trans-series ansatz. So I'm going to take a linear combination in which I will have powers of C, okay? And here, I want to assume that UL of kappa go like e to the minus LA kappa to the 5/4, okay? So in a sense, C, this constant C is a variable, it keeps track of the powers, of the order of the exponentials, okay? So this is, if you want, what you could call an Lth instanton correction in this theory. In 2D gravity, okay? And this is just the perturbative series. This is the perturbative part. And now, this is a trans-series, this is what I call a trans-series ansatz. And this is a very powerful idea that, you know, the idea is that you take the mathematical structure that you use for perturbation theory, but instead of using a perturbative ansatz to solve it, you use a non-perturbative ansatz to solve it. But you keep the same equation, okay? You can ask me why, okay? Let's think, as I said, there is a mathematical justification to this, but let's try to see what you get when you do this, okay? Because this is a very powerful technique to actually get things. So you now plug this in pan level 1. Well, of course, for U0 square, for U0, sorry, you get the U0 square minus U0, so you get the same equation. But now for U1, you will get a very nice equation. You actually get a linear equation. And this is not strange because we are linearizing the non-linear equation around the solution. So this is a linearization process. So all the corrections here will satisfy linear equations. And this is the first equation you get, okay? So you think about U0 as the perturbative background, and you think about, sorry, this is U1. U1 as a non-perturbative correction, and it's going to satisfy a linear homogeneous equation. For higher UL, you get linear non-homogeneous equations, but they are all linear, right? Now, how do you solve this? Well, let's try something very general. I mean, we want to have some sort of exponential behavior, but actually here, let me not even assume what is the power that appears here. Let me just be very general. I just want to have something which is exponentially small, but I don't want to actually ask anything else. So let me actually leave rho, A, and sigma as unknowns. Now, it's very easy to see, and it's done in the lecture notes in big detail, that if you plug these answers in this equation, and you want to have a non-trivial solution, this determines uniquely all these values. Okay? You get that A is A square root of 3 divided by 5. You get that rho is 1 over 8, I think. Yeah, minus 1 over 8, okay? And you get that sigma is 5 over 4. So this determines the whole set of parameters. So you see, you don't need to do an asymptotic analysis. Remember that these numbers, we got them from a hard asymptotic analysis because we read the location, the A we read from the location of the singularity, from the sub-leading exponential growth of the series. The factor B, we read it from the correction to the factorial behavior, right? And this as well, you know, this, I mean, well, this is essentially 1 over the Z, so this is not so hard to find. But you see, we got really a determination of A just from the equation. But of course, you know, this is just the leading order. But if you write U1 in full detail, you will get a full series of non-perturbative, of a full series in kappa. So you get actually kappa to the minus 1 over 8. You get minus a square root of 3, 5 to the 5/4. But then, just by normalizing the first term, because this equation doesn't fix the overall normalization, I get bunch of things. I get all the corrections in kappa to the minus 5/4. Okay. So let's actually summarize the situation. Now I can actually get a lot of information about the non-perturbative structure of this theory just by using the same equation that I use in perturbation theory, but assuming that the solution to this equation is going to be a Trans series. And then I get everything, essentially. I get a full determination of the asymptotics except for the Stokes constants. The Stokes constant, it's the hard core of this. I cannot determine it in this way, so I can determine its value numerically, but from this analysis, I don't know get it because, U1 has never, it's always defined up to an overall constant. But in spite of that, I can get all corrections to the U1, and then I know that the corrections appearing here, corrections appearing in the Trans-series, give me corrections to the asymptotics. So here I can actually write down by solving this equation to the next leading order, solving the equation for U1, I get the full genus asymptotics, and I get, in a sense, you can think about this as the full perturbative expansion around this instanton configuration. So this is the leading part, but by using Painlevé 1, I not only get the perturbative part, but I get all the fluctuations around all the instanton configurations that I have here. This is the one instanton configuration, but you could push this and get all instanton configurations in this way, okay? So this is a very powerful method, and if you want, you can actually check that this number, using this large order behavior and numerical techniques, you can check, you can have fun checking that this actually gives you the subleading asymptotics in that formula there. Yes, Edward?
Could you just remind me where this Painlevé 1 equation came from?
The Painlevé 1 equation, the one way of deriving is the following. You solve the double scale matrix model by using orthogonal polynomials. And then, there is a recursion relation that these polynomials satisfy. And then in the double scaling limit, this recursion relation, which is a finite difference equation, becomes an ODE. And that's Painlevé 1, okay? So it comes from a recursive solution of the one matrix model, okay? Okay, so, yeah, more questions, yes?
You had here in the asymptotics that you got from the asymptotic growth of the coefficients, you could have had both a plus and a minus sign for the exponent coming from the two poles, or two singularities on both sides. Here it seems rather weird to put both. That essentially means that L goes from minus infinity to plus infinity in this expansion of U as a sum over instantons.
Yes.
I guess that is how you'd account for that.
Here I only considering the singularities that appear on that side, okay?
Okay, I see.
Now, this is a good question, and actually there is a way of incorporating also the instantons that appear in this way by using a double ansatz for this. I could now have a double ansatz in where we have L and N, M, and then L would keep track of the negative exponentials, and N could keep track of the negative exponentials. Actually, we did that in detail, and it's a very interesting story that then was later developed by Ricardo Schiappa and his collaborators. So this is something that you can do. But physically, for determining solutions of Painlevé 1, which decay along this direction, this solution is enough. Okay? This is actually, there is a theorem of Ovidiu-Costin based on works of Ekal that says that any solution of Painlevé 1 which decays like this, which has this asymptotics at infinity, is going to be a Borel resummation of this combination. So again, Resurgence gives you a way of parameterizing all the possible non-perturbative solutions to the problem. So let me mention there are various things that I would like to mention here. So the first one is that it's related to what I just said, that here we have an arbitrary Trans-series parameter, okay? So it's normal, right? Because we have a second order ODE, we are fixing an asymptotic in one direction, so there is 1 degree of freedom left, and this is actually this number here. And as I said, there is this beautiful theorem by Costin and other people that says that every solution of Pauli-Levé-1 without asymptotics is going to be a resummation of this with an appropriate value of C, okay? Second point, very important, you see that this, you can already see it here, you see that this doesn't determine the unique solution to non-perturbative gravity. Here I did a perturbative analysis. The perturbative expansion of these U kappas or F kappas is completely determined. The perturbative part is completely determined by the expansion of this, but the solution itself is not fixed because this is second order. I just are just a fixed one boundary condition. So this freedom in determining what is the non-perturbative completion of 2D gravity is also equivalently encoded in this coefficient. And again, resurgence does not, I mean, this is a famous open problem. There is no unique, as far as I know, well, some people would jump in their seats and say, oh, I did the completion of non-perturbative gravity. But, I mean, there are works that go along that direction. In the 90s, there were many proposals of how to do a non-perturbative completion of 2D gravity. Clifford Johnson worked on this. Parisi and Marinari has another proposal, and so on. But a priori, apart from proposals, what you get just from the analysis of what people did in the double scale limit, you get that there is a one-parameter family of solutions, and resurgence doesn't solve the problem of restoring uniqueness. Resurgence doesn't tell you, yeah, the right value of C is 1/3. No, I mean, resurgence, what resurgence tells you, how to decode a general solution to non-perturbative gravity as a resummation of a perturbative part plus an infinite series of instanton corrections, which is already quite nice because it's a way of parameterizing all these non-perturbative solutions by a semi-classical analysis in which you see here the perturbative part, the fluctuations of the matrix model around, around this double scale limit plus all these instanton corrections, okay? So that was one of my observations. A second observation, a final observation is that now you can ask, what is the meaning of this? We have found non-perturbative effects in 2D gravity, and we have an amazing analytic control. We can determine the strength of, we can determine the action, we can determine the full series of fluctuations around these instantons. So what is the meaning of this? So what is the meaning of these corrections? And this was clarified in a couple of beautiful papers by Alexandrov, Kazakov, and I think Kutasov, and then a paper by Martinek. And they actually found that these things are D-branes. These are really D-brane effects. And they did a very beautiful calculation in which they say, well, this really looks like a disk calculation on the disk in 2D gravity with boundary conditions imposed by D-branes, which are these famous ZZ branes, ZZD branes, so these are samological D-branes, and you can actually reproduce this number on the nose, okay? It's not obvious that you can reproduce the full series of fluctuations. This would be a very complicated calculation in Liouville theory with D-brane boundary conditions, but what they did is actually to reproduce this not just for the 2-3 model, but for the whole series of PQ CFTs coupled to gravity, okay? So we know that resurgence in this case gives you a very precise analytic control of instantons that you discover already from the genus expansion, and these are indeed D-brane effects, okay? So I think that's pretty much everything I wanted to say for today. So let me mention just that if you want to exercise yourself on this, there is another interesting example that you can do, which is Pauli-Levé 2. Okay, this is another nonlinear ODE, and Pauli-Levé 2 is supposed to describe minimal supergravity. Huh? So it's pure supergravity. Okay, and the beautiful thing about Pauli-Levé 2 is that you can solve the uniqueness problem. There is a unique solution because there is a very special solution of Pauli-Levé 2. The story is very similar, and you can do everything. You can do also the Resurgent analysis and so on. But there, people were able to find a beautiful non-perturbative completion, and this is a very particular solution of Pauli-Levé 2, which is called the Hastings-MacLeod solution, which surprisingly appears in other contexts, like in KPZ, but not Nitniks, Polyakov, and Somologico by Kardar, Parisi, and Zhang. But it's a place where you can actually, this is a case in which you can actually fix the non-perturbative solution, which in a sense reinforces the idea that supersymmetry might be very important in order to find non-perturbative, well-defined non-perturbative completions in string theory, because pure gravity has this ambiguity problem, but pure supergravity can be defined uniquely, okay? So it's a very beautiful exercise. I wrote some ingredients in the notes, so if you want to exercise yourself with these kind of techniques, you can do pan level 2 on top of pan level 1. Okay, let me finish here.
Yeah, so my question is related to your non-perturbative ambiguity. So in some ways, the Stokes constant is kind of absorbed in that non-perturbative ambiguity from this point of view? Or would you say that I mean, you had this explicit determination from the large order behavior, but there's no way to get that.
No. The Stokes constant, what the Stokes constant would tell you is that, you see, imagine that you want to get actually something real out of this, okay? Now, you would have to do this Borel summation here, but then, you would get a contribution coming from this, okay? So then, you would have to add a non-perturbative contribution which cancels this imaginary part, okay? And this imaginary part that we do need to cancel would be related to the Stokes constant, because the Stokes constant tells you the strength of the ambiguity for the Borel resummation of this part. And, so if you do Borel resummation of this part, you have to do lateral resummations, and then you will pick an imaginary piece, which will essentially be 1/2 of this, okay? And then here, in this C, you would have to cancel this if we wanted a real solution, right? You would have to put it by hand. And then the Stokes constant would enter into the imaginary part of C in order to have a real solution. Actually, in pan level 2, this can be done completely explicitly, because there you have more control, because you know what is the solution you want to get at the end. And that's exactly how it works, okay? So the Stokes constant is important, for example, you want to impose an additional reality condition in this thing, but this doesn't fit completely C. Okay? And it's very important that, that the Stokes constant is an intrinsic property of the perturbative series, you see. It's not something that so that's why I insisted so much that you have to distinguish the Stokes constant, which is an intrinsic property of the perturbative series, from the transseries parameter, which is totally arbitrary, okay? Unless you give me some additional information about the kind of solution you want to have. For example, in pan level 2, we know what is the solution you want to get. You write these transseries answers, and this fixes the value of C completely, okay? So,
more questions? Actually, I have a question. So maybe you already explained this, I missed it, but so in the expansion of U1, I guess that also is a asymptotic expansion.
Absolutely, absolutely.
So the non-perturbative terms that you get from that corresponds to the second instanton at 2A?
That's a very good question. That's a very good question. Very good, very good. Actually, we have to write a paper to understand this. So, I mean, this was actually a very interesting thing. So you can think that the expansion around 0 gives you A, right? The first instanton and the other one. Now, if you look at the expansion here, you would say, yeah, this is the second instanton, okay? But then, the thing is that if you think that this is just the answer, then you will miss. You will not get the right structure. And this is where, as some of you were asking, I think this is where you have to really solve this with 2 parameters. If you want to understand the non-perturbative structure of this series, you really have to use the 2-parameter solution of pan level 1. So I actually wrote a paper with 3 mathematicians in order to understand this carefully, and with Alexander Itz, which is an expert on Riemann algebraic problems, Stavros Garoufalidis, and Andrei Kapaev, who is an expert on pan level 1, and we actually explain how this problem is solved by including by using a 2-parameter transseries. So if you want to understand the asymptotics of the perturbative series, the standard instantons are fine. But if you want to understand the asymptotics of all instanton sectors, you have to include also the negative instantons, the instantons with positive action, okay?
And so another small question. So once you have figured that out and you have the U1, the U2, and so on, then you have to sum over L, or maybe you have the two parameters.
Yes.
So I didn't understand, so what happens to that sum?
Yeah,
is
that's
that
a very good question.
or?
That's a very good question. This is where, there is a potential, worm can, right here, right? Because how do we know that this sum, I mean, okay, you do Borel summation of here, you get a number, you get Borel summation of this, you get a number, but how do you know that this sum converges? Well, in this case, this was proved as a theorem by Kostin. He proved that if Z is large enough, you can actually, this sum is not only well-defined over all instanton sectors, but actually matches the exact solution of Painlevé one with this boundary condition, and then, for that value. So in a sense, this is not only well-defined, but it parameterizes correctly all possible solutions of Painlevé one with this. But I agree with you that this is a very important question, and this is, you see, there are many sources of infinities in quantum field theory and in quantum string theory. One source is renormalization. The second one is the asymptotic property of the series. But the third potential source of infinity is the sum over the instantons themselves, right? It's an infinite sum. In this case, this is under control, but there are indications that maybe in quantum field theory, for example, this is no longer the case. That this series also diverges and you have to do something else.
More questions? Okay, if not, let's thank Marcos again. So, Marcos,